Welcome to Galileo Science Cafe. We are delighted that you are with us tonight. We always ask the Galileo Science Cafe attendees what they would like to hear about. And this topic was the top on the list, and for good reasons, and I think, even more so as we're hearing more and more news. It's very timely. I'm very excited to present COVID Mythbusters, and our COVID Mythbusters at Mason are Dr. Lance Leota and Dr. Padu Seshire. Before we begin our session, I want to tell you a little bit about Galileo Science Cafe, if this is your first time dropping in. Normally we have it in September through May, except for December and January. And we have it in person, as you can see in the pictures on our screen. It's a very informal affair where attendees, like you, can ask questions and interact with the experts to just talk to them about their research or ask them questions. And we will have a session where you can network and interact as closely as we can with the experts at the end of the session. So what we'll be doing tonight is to have a presentation first by Dr. Leota and then by Dr. Seshire, and then we will alternate some of the submitted questions with any questions that you all want to type in to the Q&A. My name is Andrea Cobb, and I direct the Galileo Science Cafe. I'm the Director of Student Research for the College of Science at George Mason University, and very glad to have this on one of the things that I love to do best as part of my position. Every year, Galileo Science Cafe showcases the latest scientific and medical discoveries in a way that the public is receptive to and can hear. As I mentioned earlier, we solicit ideas from the attendees, and past topics have included robotics, global climate change, the environmental impact on the Potomac and surrounding tributaries, artificial intelligence, cybersecurity, autonomous vehicles, cancer, bioterrorism, antibiotic resistance, and vaccinations. Like I said, we usually have this in person, and so you can see the pictures here. Hopefully we will have this once we resume normal operations, and we include a light dinner. It's all free, as well as a social hour preceding the scientific presentations. And then we have, again, a Meet the Scientist and networking reception. We often ask related researchers and members of the research team to come and talk to you and talk to them about what it's like to be a researcher at Mason or answer any other questions. It's a great experience for students that are interested in research. Whether you're in high school, college, or graduate school, you're going to find something that you find fascinating. All right, so let's go ahead and start with our sessions. There we go. All right, so here are our two experts, Lance Leota, MD, PhD, and Padu Seshire, PhD. I'm going to introduce Dr. Leota first. He'll have his talk, and then I'll introduce Dr. Seshire, and he'll have a presentation as well. Dr. Lance Leota has been at Mason since 2005 as co-director and founder for the Center for Applied Proteomics and Molecular Medicine. Before that, Dr. Leota was chief of the Laboratory of Pathology at the National Cancer Institute, the deputy director of the National Institutes of Health, and co-director of the National Cancer Institute FDA Clinical Proteomics Program, and director of the Anatomic Pathology Residency Program. He has a PhD in biomedical engineering and developed the first mathematical model of cancer metastases. He has invented, patented, along with his co-workers, whose work you'll be listening and learning about today, transformative techniques in the fields of diagnostics, like COVID diagnostics, cancer therapeutics, and other kinds of analytical equipment. One of his inventions, the laser capture microdissection prototype, is in the Smithsonian. So how wonderful is that? Wouldn't you love to have something of yours in the Smithsonian? His team, who has been working very hard during all of the shutdown to come back up to the lab, socially distancing and performing their experiments in very careful and strategic fashions. His team at CAPMM studies human tissue, cultured cells, and body fluids with novel technologies. They have clinical trials at George Mason. You may not realize that. And he is the founder of Theranostics Health and Series Nanosciences, which develop important innovative tools. Dr. Leota and his team recently received FDA approval for a COVID-19 test that he's going to tell you about tonight. Dr. Leota has more than 100 issued or allowed patents and more than 690 publications. He is an ISI highly cited investigator. In other words, he is the expert's expert. So let's see what he's got to say.
Well, we're really thankful, Andrew and I and Padu, that you're here with us tonight. And we hope to see you in person in the new year when Galileo Cafe starts up again. But tonight we're going to be talking about coronavirus. And as we all know, coronavirus deaths continue to surge worldwide, and we're now entering the winter seasons. We all worry about that. But the good news is that scientists are slowly figuring out how the virus works. And we are more successful as doctors at treating patients with conventional therapies compared to the beginning of the pandemic. And promising data, as you might have read about in the newspaper, offer great hope that vaccines will be coming soon for individuals at risk. Nevertheless, we understand and we know that fear, worry, and uncertainty about the pandemic influences every aspect of our lives. Our goal in this session is to provide scientific truth and hope about COVID so that you and your family can steer clear of viral myths that unnecessarily add to your burden of worries that you already have. So we're going to try to answer some of the key questions that our citizens of the Commonwealth have been asking us over and over again about coronavirus. What is coronavirus? Where did it come from? What are my chances of dying? How will society adapt? Will I die if I get infected? Can I get tested, and which test should I trust? If I recover from COVID, will my antibodies protect me, and for how long? And what new therapies are on the way? And when will a vaccine be available? And should I take it? We're going to cover these questions in 20 minutes, so we're going to go quickly, but we'll try to cover all these important questions. We know that COVID-19 is far deadlier than the flu, as shown here over time. We can see here's the deaths, weekly deaths due to COVID-19. Here is the weekly deaths due to the flu. We can see that the total deaths over the past 10 months have been much higher than we would expect without the COVID. So COVID has been adding an increased toll of deaths across the United States and across the world. And as you know, it's currently surging and on the rise in the United States. Well, what is COVID and how does it work? First of all, it is a member of the family of coronavirus. That's like a cold virus. And the virus is a shell that has all these spikes on the surface of it. And then inside that shell is the RNA, which has the information to make more viruses. And these spikes are the way that the virus sticks to your patient's cells and allows the virus to get inside the cell. Usually, coronavirus infects through the lungs. You breathe it in, and these spikes are used by the virus to stick to receptors on the surface of your lung cells. And when this sticking happens, when the virus sticks with the tips of these spikes, it then enters the cell and it opens up and releases its RNA. The RNA gives instructions for the cell to produce billions of viruses which exit the cell. Now, when the cell is making all these viruses, it is screaming out in terror. The cell And that's stimulating immune cells to come in and react to that damage, causing what's called a cytokine storm. That's what causes all the damage to the organs, the fever that you feel, the aches and pains like a flu. That's caused by the immune hyperreaction to the virus. The reason it's important to know that there's these two aspects is that antibodies, vaccines, and antiviral treatments, they might work early on to prevent the virus to get in the cell and start the infection. But once there's a big inflammatory storm raging, then that's when steroids, antibiotics, anti-inflammatory therapies are working. Let's talk about how the virus gets into your lung and causes all the problems. Well, when you breathe the virus in, it goes into your air sacs of your lung, where you exchange oxygen with your bloodstream. And in these air sacs, the lining, which is very thin so that the oxygen can get across into your bloodstream, the virus sticks with its spikes. And when the virus irritates the lining of these air sacs, it produces big irritation, and fluid pours out of the blood vessels in the wall of these vessels of the air sacs. So all of a sudden, fluid starts accumulating and suffocating the patient because you can't get any oxygen through this fluid. And if, let's say that you had half of your lung compromised by chronic obstructive pulmonary disease or some other chronic problem, you can see if half of your lung is filled up with the fluid, unless you have a lot of extra lung capacity, it's going to cause severe problems. And that's why people can't breathe, and that's why they need to be treated to give them more oxygen. If we look at under the microscope at the lung of somebody infected with COVID, we see that the normal lung tissue has these big airways that I said that are all open and clear, where you're breathing and exchanging the oxygen. But here is a COVID lung where you see all this fluid building up. Instead of this white space, this pink fluid is filling up everything. And you see these red plugs of clotted blood in little vessels of the lung that are blocking the blood flow in the lung. And also blood clots happen in other parts of the body. And then inflammatory cells fill up these air sacs. So you have suffocating fluid and inflammatory cells pouring into the lung. That's where the problem starts. Now, we used to think that all of those patients should go on to ventilators. And in the beginning, we put more patients on ventilators than we do nowadays. And we saw that many of the patients who were on ventilators had a poor outcome, low survival, and particularly in the older patients. We now realize that we do not need to treat as many people with the ventilators. If we keep them off the ventilator, it's better for as long as possible. Instead, if we can treat them with getting other ways to get oxygen into their lungs without putting them on the ventilator, which breathes artificially for them, because then it's hard for them to get off the ventilator. So we've made tremendous progress in how to treat COVID with conventional therapies, and we know only in severe cases that's when we need the ventilator. Otherwise, oxygen treatment, even treatment at home, can really make a difference. Will you die if you catch the coronavirus? We all worry about that. If we look at the data based on age and on underlying health conditions, we see that young people have very low chance of dying. For example, in the state of Virginia, I think there's only been one individual less than age 29 that's died from coronavirus. But the job of the young people who are relatively safe from dying, their job is to protect everyone else by not transmitting it. As the age goes up, we see there's a higher chance of dying, up to 10%, but it's as highly influenced by cardiovascular disease, diabetes, respiratory, and high blood pressure all have an effect. there is not a significant evidence that autoimmune diseases increase the death rate. And so when we think about the time course of coronavirus, first is onset of symptoms, then day 4 to 9, the lungs fill up with fluid, the virus goes into the blood in 10 days. And so the first 10 days to 2 weeks is the most significant period. There's no significant definitive evidence that you can catch it again if you already caught COVID, even if you're asymptomatic and you got over it. There's really no good scientific evidence that you have a high chance or virtually any chance of getting it again, because the antibodies that you produce are highly effective, as I'll show you, and there's no definitive scientific study that shows a second infection is not just a chronic long-term version of the same original infection. We don't really have much definitive evidence that it's a new virus that came in to infect you and not the virus that's just been sitting there in your body. So try not to worry that you can catch it again if you got sick with coronavirus once. And after your antibodies are generated, they will surge, and then your immune system will memorize the virus and never forget it. And so whenever you're exposed to the virus again, the immune system will rapidly go into react and produce antibodies all over again. So your immune memory should work just as well as it works for the common cold virus. So that's why if your antibodies are developed naturally, or if you develop antibodies based on a vaccine, there's high likelihood that you're protected. Where did the virus come from? Well, 60 to 75% of our new infections and pandemics come from animals, viruses or bacteria that travel transmitted from animals to people and then go from one person to the next. We think maybe bats are rare, but there's many species of bats all over the world, and they often are a vector to transmit viruses to animals and then to people. This coronavirus was first sequenced in a bat, found in a cave, and then that virus sample was brought to Wuhan. There's 2 types of testing for COVID-19, 2 kinds of information that you can get. Are you infected now, and can you shed the virus to others? That's a test for the antigen or the RNA in your nasal cavity or in your oral fluid. Or were you infected in the past and now have antibodies that can attack the virus? So a virus test or an antibody test, they test 2 completely different aspects of the disease. You can do virus RNA testing with a nasal swab, but now it seems to be more convenient to be done by, instead of putting the stick deep into your nasal cavity, we know you can just swipe the outer nostril and that will be just as good, or you can spit in a cup and that'll work just as well. You hear about the term COVID PCR test. What is a PCR test? That simply means that you're isolating the RNA from the virus in your oral fluid, saliva, or nasal secretions, and then you're amplifying it. You're copying it over and over again, and each time you copy it, go through a cycle. It's a certain cycle of amplification. It takes more cycles of amplification to see the virus RNA if there's not very much of it, but it takes only a few cycles of amplification to see it if there's a low amount. And so we can look at how fast the virus comes up when if at all, if we amplify it, and that's how we can use PCR to test the virus. It's thought that the PCR, the RNA amplification test, is the most sensitive way, but more sensitive ways are coming. And in fact, each virus particle makes thousands of copies of proteins. And so, we think also looking at the proteins produced by the virus is going to be another really sensitive method, and it will tell you what the virus is doing. The second type of testing is antibody testing. And that is where you take a sample of the patient's blood, or antibodies are also present in saliva, and then you can measure the presence of antibodies to see if they have risen up in your body to protect against the virus. If we look at the timing of all this, you can shed the virus to others 2 days before you start having symptoms. If you're going to have symptoms, as you know, some people have no symptoms. And then you have 2 to 5 days when you're shedding the virus and can infect others before it starts going down and your antibodies come up and start protecting your cells against more viruses being produced. And so depending on what point in time, you might have a high value for the virus or a high value for the antibodies. We think that the antibodies that your body makes that are highly effective are the ones that stick to the tip of these spikes. Because when they stick to the tip of the spikes, they prevent the spike from binding to the surface of the cell and getting into the cell. So that's why a lot of the vaccines that you hear about are made against the tip of the spike. When we looked at antibody testing for the virus, we found that some of the early first antibody tests that came out were not very sensitive at all. We missed a lot of people who really were actually infected in the past, and were not very specific. We might have picked up antibodies to common cold instead of against COVID-19. So we set out to develop our own very sensitive, extremely specific antibody test, and we freely received visitors. Anyone can come in and get tested for the antibody in our CAP-CLIA certified laboratory. And our test is 97% sensitive and 100% specific. This is our team. So we have a really good antibody test that's very sensitive and can pick up patients, and we can easily measure antibodies produced in, for example, healthcare workers who are completely asymptomatic, but obviously they must have been sick with COVID at one time. So the big question is, do these antibodies do anything? Did they affect the virus at all? So we set out to answer this question. And what we did is we took the patient's blood that had the antibodies in it, and we simply mixed it with the hot virus in a special high security lab called a BSL-3. This is done by Dr. Narayanan. And the virus usually kills cells in the dish, making big holes and plaques, as you see here. But when we added the patient's antibodies, it completely blocked the virus from infecting the cells. But the most fascinating thing about what we found with our patients in the trial is that many of them made super antibodies that stopped the virus even when they were diluted 1 to 10,000 times. 1 to 10,000, that's a big dilution. They completely killed the virus anyway. So we think there's a lot of antibodies that are produced by patients who have naturally infected that could serve as a new therapeutic direction for new therapies. And so we also asked, do our patients who make these antibodies against coronavirus, do the antibodies stay around? Do they persist or do they go away? You've heard worries that the antibodies are just gone pretty soon. Remember, even if the antibodies go down, the memory of your immune system remembers them, and they remains ready to fight. If you kept the antibodies for every sickness you ever had, your body would be filled up with all those antibodies from all the viruses and bacteria you had in the past. Instead, antibodies go up, and then they're transferred to the memory. But we find that our patients have antibodies that neutralize the virus for at least 5 months in some patients. They continue to neutralize the virus. Very hopeful, very significant. And interestingly, another unexpected finding is that we find that patients have new kinds of antibodies that we never expected that are not against the spike protein. They're against other proteins. In fact, here's an example of a really strong antibody that a patient has that's against the receptor where the antibody is binding. So the antibody, where the virus is binding. So this person's body made an antibody that blocks the virus from going into the cell. And so these have really profound implications for new treatment approaches. In fact, we now have a new test where we can measure somebody's blood, the antibodies in their blood, and we can say, you have super antibodies and you should be the one to donate your blood to help someone recover who just got COVID. So this is very helpful because we know that we can use convalescent plasma, people who recovered from COVID, and give their blood to somebody else to help them. But sometimes it works and sometimes it doesn't. We think we can predict who's going to have the powerful blood as a new weapon against COVID. And we're going on to actually mass produce antibodies exactly like the antibodies that we found in our patients, because we can use a special culture system that takes human antibody producing B cells, and we can produce large quantities of human antibodies and use for therapy. Like you've heard about antibody therapies that are been out there, but they're against the tip of the spike protein. We are going to have antibodies against other categories of the viral infection that can inhibit it in other ways, making even better or better combination therapies for patients. Our laboratory, as a CAP-accredited diagnostic laboratory, conducts both antibody testing, but also antigen testing. That is the protein of the virus and the RNA of the virus. So we've been helping the university do surveillance of asymptomatic students and athletes using both of these types of tests. And we're ramping up at the request of our new president to scale up to do thousands of students per week. It's a big job, but our team is scaling up, ready to do it. We're also looking into rapid antigen tests that you can read by looking at the result, because the PCR test, the viral RNA test, takes, at least in our hands, 3 hours to do. Even if we can do hundreds at once, we have to wait 3 hours to get the results. And in that time, the student or the citizen could be spreading the virus. The ideal future of testing, and this is what the NIH says and all scientists around the world say, is to have a rapid visual test or electronic test that will give you in 15 minutes whether you are positive and can infect someone else with the virus. At that point, you have a positive test, like a positive pregnancy test here. You can then quarantine the person, do contact tracing, do medical follow-up. At the same time, with the saliva test, the rest of the saliva you can send to the lab and confirm it with a PCR test, so you're absolutely sure of a correct diagnosis. And that way we don't make mistakes, but we quarantine individuals as soon as possible. So that's what we're testing, developing, and completing all of the FDA required data for, because we think it's just going to the testing is only get better and faster. We also are looking into wastewater sampling for early warning of COVID-19. People who are infected with COVID shed the virus in their poop, and it ends up in the wastewater, in the toilet, and then in the sewer. And we're collaborating using our special technology that we developed that captures the virus and enhances the sensitivity dramatically. That was licensed to Series Nanoscience and is now used in all the LabCorp testing that is done. We can use that to concentrate the virus in the sewer, and we find that can be used to monitor when the virus is appearing in a city. And we can see hotspots in the city as they develop and predict them 2 weeks ahead of time before everybody starts getting symptoms. So it's a very promising way to monitor surges in the virus in society, in nursing homes, in neighborhoods by just looking at what's in the sewer. We're going to try to do this in Mason by sampling wastewater that's coming out of the dormitories and using that to focus our surveillance on those dormitories that have evidence in the sewer that the individuals in the dormitory are shedding the virus. Very exciting concept. And universities and institutions all over the world are attempting to do this. Another important question that everyone has is, when will we have the vaccine? Well, as you've heard many times, probably, it usually takes greater than 10 years to have a vaccine. All the other vaccines that we've developed have been taken extended periods of time, and 3 years usually for each phase 1, phase 2, and phase 3 studies to be done, which is first initial testing, then safety testing, validation. However, with all the competition of companies working on viral vaccines, and with the enormous effort that scientists all over the world have put into sequencing this virus genome, the RNA, and then making viruses, as you know, we have 2 promising vaccines that have just gotten to the claim of greater than 90% efficacy, even in aged individuals, and those are from 2 companies, Pfizer and Moderna. These vaccines made by these companies are RNA vaccines. This is different than a whole virus vaccine like you might have for polio. It's a piece of the RNA, same kind of RNA that the virus has, and goes into a cell, and so then the cell produces only that little piece that RNA generates of the viral protein, spike protein in this case, and then that generates antibodies against it. And it seems to be very promising. So this offers a lot of hope, but what offers even more hope is that you have all these competing companies and they're all trying to develop a vaccine as fast as possible. So we hope that soon you'll have many vaccines to choose from, but they should go to the elderly and the most at risk people first. In the meantime, while we're waiting for that vaccine, masks are very effective. They decrease the chance of getting the virus 100 times in some studies, particularly when matched with social distancing. So that is the best way we can fight the virus now, and we can't just relax because we think a vaccine is coming. But science is bringing all these new developments, in addition to new antibody tests, new antivirals, new antibody treatments, as we talked about, in addition to the vaccine. And we know that we can reduce that inflammatory storm that I told you about with simple steroids or other anti-inflammatory medications. So there's a lot of hope because there's many ways to treat the virus at different stages of the disease. Nevertheless, everyone is justified in the worries that they have, And the top three worries of the Gen Z and millennials, because we're talking about the students in our campus, is they're anxious about hospitals being overrun. They're stressed that the viral outbreak will trigger an economic depression, and they're concerned that someone they love will die from it. And so our young people have, we are blessed with our young youth. They have such a good attitude about fighting this pandemic. In conclusion, what is the effect of the COVID-19 pandemic on science and society? Well, the positive impacts, we hope, is that the vaccine and diagnostic technology is accelerating tremendously, and competition drives innovation. More young people, we find, want to choose a career in science and medicine. They want to make an impact on the health of society. And I think everyone knows more about viruses than we ever thought we wanted to know. And we hope this will cause increased visibility of scientists as role models. On the other hand, the negatives are that medical and scientific progress on non-COVID-19 urgent questions like cancer, opioid epidemic, climate is shut down, that universities, graduate schools, medical schools are hampered physically and financially, and we can't make the progress we want on curing cancer. False information, trolling, and changing guidelines from leadership with gain of new knowledge, which you might think is normal, causes increased fear. And in some sectors, there's greater distrust of science, not more trust of science. And that's why we're having this discussion. Finally, what can you do to help fight COVID-19? Be a source of truth about COVID-19 for your family, friends, and school. Keep up to date with the science. Become a mythbuster for COVID conspiracy theories. Promote peer-reviewed articles as the only reliable information, not rumors. And be a source of hope, a role model for the value of scientific truth, because everyone is a scientist. Thank you very much.
Thank you so much, Dr. Leota. That's so helpful and so interesting, and I can't wait to see what questions that you'll have to answer shortly. I do want to give a shout out to Michael Galvin, who is a partner with me in this event. Michael is the Associate Director for the Regional Campuses for University Life, and he is working very, very hard to have a wonderful environment for our students who are on campus or off campus, and make things as positive and important and exciting and safe as they can. So thank you, Michael, for joining us in this effort and supporting all the mischief that we get into. So thank you.
Thank you.
Yes. Our next speaker, Dr. Padu Seshire, is a tenured professor of mathematical sciences. You may think, math? What does math have to do with the COVID epidemic? Well, I will tell you that all of those predictions that you see and the graphs and so forth, those are developed by mathematicians, of which Dr. Seshire is an expert. He is like I said, he's a tenured professor of mathematical sciences at George Mason University. He is the Associate Dean for Academic Affairs and Director of the STEM Accelerator at George Mason. One of Dr. Seshire's passions is communicating science with students and for students, and he is an expert teacher. He can communicate very complex things in a way that makes them accessible and understandable. So we are so excited to have him today to help us. Again, Dr. Seshire is also an expert's expert. He has received multiple grants from several agencies, including the National Science Foundation, the National Institutes of Health, the Whitaker Foundation, the Texas Advanced Research Program, the Virginia Department of Education, and State Council for Higher Education, and probably many, many more. He contributed extensively to teaching and has won a number of prestigious awards, including the President's Excellence Award in Teaching, which is the highest award offered for teaching at 2 different institutions. He's always enthusiastic. He's always positive. He has been nominated for the Presidential Award for Excellence in Science, Math, and Engineering. He has delivered keynote and plenary talks at many meetings, international and national. He's one of the Nifty 50 speakers and has spoken at the USA Science and Engineering Festival, which some of you may have attended. He's also given 2 TED Talks, which you may look up online. And he has written 2 books about mathematical modeling. So check Amazon. I don't know if those are on Amazon or not, but I'd like to get the one for mathematical modeling for teachers. I think that would be fabulous. He was elected as both a new counselor for math and computer science on the Council for Undergraduate Research. And he is in the U.S. National Commission for Mathematics Instruction by the National Academy of Sciences, all very prestigious bodies of experts. So he is master teacher. He has mentored projects with high school and undergraduate students and graduate students for years. Let's see, I counted up. I think he has been a mentor for 7 or 8 years in the Aspiring Scientist Summer Internship Program. And I think he's going to show you some of the mathematical models he did with those students. He has global partnerships for people in over 15 countries with student and faculty exchange. And one thing that Dr. Leota, I don't know that he emphasized, but part of the reason that they were able to work so quickly on their research was because they had international partnerships with Italy and had done a lot of work there. And so they were able to get all kinds of materials that they needed for their research. So these international programs are super important. And so he's been in many invited talks. He's been in lots of news stories. He has been a program director at the National Science Foundation. So let's welcome Dr. Seshire to hear about mathematical modeling of COVID and other epidemics.
Thank you, Andrea. So that was a long introduction. Thank you. I'm very happy. Well, I'm actually happy to be here and share my excitement and things that I've been fortunate to learn myself in the last few months. So, I do like to interact with the audience also. So I hope you will engage with me as I ask some questions. Hopefully I can see what you're chatting to. As the first slide suggests, there's a lot of these partners, and I'll talk about some of them in just a second. They are either organizations that I've worked with or programs and initiatives. For example, the ACEP program that has given me the opportunity to mentor students, and then also, funding from different agencies like the NSF and the NIH and the Department of Education. So I want to make sure that the audience will leave learning some new things, and I learned quite a bit from Lance's talk. It's amazing how he's also able to deliver something as complex in a very, very systematic and way, so that we can go back and think about more questions, and how we ended up with the science being so important, asking the questions over and over again. That's very important. And the same thing appeals to models too. So let me start off by asking in this crowd, I see there's over 100 people here. There is a picture on the right, not me, but the other side with all these colored things. Can anyone recognize what that is? And if you can you type on the chat, please, very quickly? Linda is saying we do not see Dr. Seshire. Okay, I guess you don't see do you all see my slides? Oh, there. Tom Hutchinson, I somehow know Tom, and UNSDGs, Alonso, great. So fantastic. So I'm glad that, you can see, like, of the 100 people, at least 2 of you know about the SDGs. This is the United Nations Sustainable Development Goals. And I'll talk about how this actually plays because we actually wrote a paper on how COVID impacts all 17 goals posed by the United Nations. And these goals are posed at a very high level: poverty, hunger, gender equality, quality education, good health and well-being, clean water, all those different most important challenges, but how this COVID has impacted everything, and mathematical models have evolved around that also. So congratulations to the 2 people that I've identified the SDGs. SDG stands for the Sustainable Development Goals, and I'll talk about it again as I go through it and how it impacts all areas. So as a modeler, I try to classify the things that I do into into computational modeling. You may imagine sitting in front of a computer and simulating nice pictures and graphs. Theoretical modeling, basically paper and pencil, and actually deriving, formulas, theorems that actually will predict things. Experimental modeling, where I have to work with people like Lance, for example, who are experts, and I cannot claim to be an experimental person who can be in the lab, but I can work with them to actually understand what the data is suggesting, is predicting, is helping prescribe. And this is where models start to get the name from descriptive models to predictive models to prescriptive models. So this is how, if you're a data scientist, you are living in the predictive world. If you're a data scientist plus you're working with policy, then you're going to be starting to prescribe things and things like that. And if you're just a modeler, you're probably doing descriptive modeling. And then one of my biggest passion, STEM education, and what are models around it. I'll say some examples around that also. And so I want to start off with, because the previous talk was on biology and mine is going to be about mathematics, I'll try not to actually talk about equations and all that too much. This is not supposed to be a technical talk, but it's going to be something that I can share in terms of understanding how mathematics and why mathematics can help explain real world phenomena. So here's the real world phenomenon. You have a petri dish under a microscope and you have bacteria in it growing. And we have been talking about viruses, but I'm talking about, let's say, bacteria. So the bacteria is growing and it's a patch, it grows as a colony. And as it grows as a colony, obviously you're not going to get a square or a rectangle or a triangle. And often the area of the bacteria tells us about the number of bacteria. So I've asked many teachers, many educators, how do you actually tell me that there's 200,000 bacteria in the petri dish? And often the response I get is, oh, I put it under a spectrophotometer. I say, what does a spectrophotometer do? Well, it actually just tells me back a number. That's right, that's great. So I wanted to go one step further. What is it actually modeling? Well, it turns out that when you put it under a spectrophotometer, the light intensity that falls on the bacteria, it takes the ratio of the intensity of what's inside the petri dish with the bacteria and without the bacteria. And believe it or not, there is a negative logarithm in front of it. And when I say that, most teachers come and tell me like, wait, logarithms, not teachers, but students say, well, logarithms have applications? Yes, they do. They help you count bacteria, for example. So I think these are types of important things where models really play a very, very important job. So in this case, you are talking to a middle schooler and say, how do I find the area of that bacterial colony? You open a textbook and it's only triangles, rectangles, quadrilaterals, and all these standard shapes. So how do you go about finding something like this? And this is where modeling, the idea of modeling starts to begin. It's like when you want to solve problems for which you don't know the answers to. And so here is a simple problem, so if your experimentalist trying to determine something in the lab and the mathematician trying to help estimate the count, right? So that's where modeling starts to begin. So recently I was able to connect mathematics and biology on using a modeling framework, how mathematical modeling framework connects with the scientific methodology. So, if the two frameworks are very, very, there's lots of things that are very close to each other. Everything from observation around you, theorizing something, that is hypothesizing in the science, for example, formulating a model for mathematicians. So designing an experiment, that is for the science of in the scientific method, to analyzing and simulating on one side, to performing an experiment. So if I were to put me in a box and Lance in a box, this is the type of thing that we both are doing. Of course, we both do interdisciplinary work also. And then, of course, I want to validate results. He wants to analyze the data and validate what is going on. And then I also want to predict and revise what I just found. At the same time, he wants to also conclude and revise the study. So this idea of matching these frameworks is very important. People just come up with all sorts of frameworks, but at the end of the day, these things are all very well connected. So one of the things I try to do is to connect this. And COVID was a great way to actually even take examples of what happens in COVID to actually understand these two frameworks. So that's kind of an educational type understanding of modeling, for example. Now, one of the most common things that you probably have become experts at is this thing everybody talks about: susceptible, infected, and recovered. So SIR, as it's called. Now, as I said, I won't do too many equations today, but I'll do at least this one because it's one of the most famous fundamental ones when any infectious disease is spreading. So when it's spreading, most of the people are susceptible. That's the S. And then some of them get the disease. Those people are infected. Now, those people then go to the hospital or get some medicines and they get recovered. That's the recovered, R. So you got the S that gets transformed to, some of them become I. And why do they do that? Well, the S people come in contact with some infected people. When they come together, it depends on how many times they come in contact with. It depends on, is the contact enough to actually transfer the disease? So that's the transmission rates. That creates the transmission rates. It's a mathematical observation. And then, of course, thank you very much, Alonso. It's coming. That's exactly right. So I want to say why, this was one of the initial models, and perfect question from Alonso. And then infected people become recovered at a certain rate. Now, I use the word rate. And when I use the word rate, you probably recognize, wait, I heard this back when I was doing calculus, something called related rate. That's exactly right. How a quantity changes with respect to time. That is where Newton spent all his time on inventing lots of things in calculus. We call that a derivative. And when you take the derivative or rate of change of a certain quantity with respect to time, we call that the dynamics. And we can write down the dynamics of the susceptible. We can write down the dynamics of the infected. We can write down the dynamics of the recovered. But it turns out that they are all what we call as differential equations. So essentially, without explaining, the mathematics, what you're seeing in this thing is you see that the susceptible people are decreasing, and therefore there's a negative sign. The S is the susceptible people that is meeting a fraction of infected. That's where the I divided by N. So this is the only time, as I said, I'll do a little explanation of the mathematics, but I'll tell you why these are important, like what Alonso just posed a myth there. So essentially think of, a group of people moving from one compartment to another compartment. I use the word compartment. And this is why these models are called compartmental models, because these are compartmentalized and people are moving from one group to the other. Now, this type of a model was created by two people by the name Kermack and McKendrick in a series of papers in 1927, 32, and 33. They worked with another famous person. His name is Ronald Ross. Many of you know Ronald Ross for his Nobel Prize for helping us understand the path of malaria, and so the cycle of malaria. So this was one of the initial models that was created in mathematical understanding disease dynamics. And so they applied this to influenza. There was this very famous London boarding school application that every mathematical model has to actually use as a benchmark. Now, what do you do with this? Well, you study the dynamics, which means you plot them, basically. You get graphs. So you get graphs for susceptible going down, then you see infected going up, and then you start to get a peak, and then somebody finds a medicine or things like that, and they start to come down, and then you have the recovered that goes up. So that's the general idea. So now Alonso asked a very important question. What about death? Of course. So you can't assume that people won't die for other causes, natural causes. You can't assume, you have to assume that people are going to give birth. So you got to include vital dynamics. So yes, it has to be, one has to actually, but before I go there, one of the most important thing is like everybody now talks about it, the R naught, what is called as the basic reproduction number. We'll talk about that later, but what you notice here is that R naught has to do with beta, the ratio of the transmission rate to the recovery rate. Recovery is going to the hospital and all that. So if you can imagine, it's just a fraction. If you increase the numerator and decrease the denominator, that's danger, because it's going to be more transmission. So the best way to not spread a disease is to keep the fraction very, very low. In fact, you want to keep it less than 1 if you can. The only way to do that is make the transmission very small, which is the numerator, and make the recovery very big. Find vaccines, find lots of things and things like that. So, and that is a very simple mathematical principle that people are after, is the R naught. So now that you understand something about models and all that in terms of the SIR, clearly there are other diseases came about like gonorrhea, syphilis, sexually transmitted diseases, which goes from susceptible to infected back to susceptible. In fact, people are talking about COVID being an SIR and then back to S, susceptible. Can you get the disease again? So then the model is there for that. And then, of course, people are exposed right now. They are not getting the disease. They immediately, they're exposed for some time. The disease is in the body, but you're not showing symptoms and things like that. So one has to add an exposed. Now you got the SEIR. So it became so popular, then the people started to, then as I said, one has to incorporate deaths. Even though I don't have the picture here, one has to make sure that you incorporate vital dynamics into these models. So these are, I won't call it myths, but these are things, it becomes myths if you actually don't assume these things and all that. And then of course, a mosquito enters. And so now the mosquito starts to bite infected human, sucks the blood and becomes infected mosquito. Yes, there are healthy mosquitoes if you did not know. So these healthy mosquitoes bite the infected individual, becomes infected, and then goes and bites a healthy individual. And then, so this is kind of, in a short way, thinking about malaria. And then you got chikungunya, dengue, and all these diseases. And then, then obviously these mathematical communities are working as two separate communities. You got like these communities that are talking about sexually transmitted diseases, diseases that pass only by direct transmission. And then there are these communities that talk about diseases that are through vector-borne or through a mosquito or a sandfly and things like that. Now, this is the unfortunate thing about research. These communities sometimes don't talk to each other. They have separate conferences, separate meetings, separate models and all that. Then we have to wait for a disease like Zika to come and then blow everybody off and say, wait a minute, guys, you better collaborate. You better collaborate because now here is the same disease caused by Aedes aegypti, the mosquito that causes chikungunya and dengue. It can also be transferred through sexual transmission. So somebody has to really come from outside like a disease to tell us how to come up with a new model. So I want to tell you how these models are evolving. And this is exactly how one of the students this summer, believe it or not, high school student from the ASIP program came and said, Dr. Sesher, what about human behavior? I want to do something in COVID, but what about human behavior? We can do all the modeling. And what if the humans don't follow the rules? I said, that's brilliant. That's exactly what nobody knows how to do that. And guess what? I'm very happy to announce to you that her full model is getting ready to be published in a peer-reviewed journal. This is one of the students from the ASIP program, but you can see how elaborate her model is, goes from susceptible to exposed. And you can see there is a transmission rate and it's a function of a behavior of an individual. The first time it's being modeled and it's going to be, I'm happy to share once the publication comes out. And then the exposed goes into susceptible, infected or symptomatic infected or asymptomatic infected. And then you have the symptomatic people going to quarantine. That's the Q. And the quarantine can go to recovered. And then the asymptomatic can also go to recovered. And the quarantine go to hospitalized and then death. You can see how you can keep making these models fancy and fancier and fancier and fancier. But this is going to be published. And as I said, I'll be happy to share our findings. It is the first time we are creating an implicit model for this. And it's fantastic. This student is only a sophomore and going into from the governor's school. So another student wanted to do, some hi-fi simulations. And so this student worked on what happens when you all get back into an aircraft. Are you going to sit next to the person who does not wear a face mask and is going to start coughing? And you are actually seeing the droplets that are coming out of their mouth, which is being forced by like a flow from the AC vent up. So what you're talking now is, and then it's slowly coming towards you. So what you're talking about is the fluid dynamics, which is from the vent. So that has equations. The scalar transport of the droplets. These droplets are different from the aerosols in other diseases. These are heavy droplets. So you got to model how they move. And then the epidemiology. Once the disease is on you, then you got to work on an epidemiology model. And then there is this airborne infection that can spread all over the aircraft or hospital wards. And then you got to study this under a deep learning framework. This is what we got funded for from the National Science Foundation through what is called as a RAPID grant. So I was also very excited when I got selected as one of the 7 experts by the International Science Council, which is above all the national academies. I represent the United States. There's people from New Zealand, from Canada, Turkey, 7 countries. I can't remember all of them right now, but we are all coming together to think about what is going to be the digital future for digital education. So we are trying to come up with some kind of a resource repository that can help everybody in terms of building character, building access, building resilience, and all these different things. There's this picture that shows there is a primer that has been created by this group which is blessed by the International Science Council, and it's now used by the National Science Foundation and all these different groups. This report is available. Feel free to you can go download it from there. So another thing that I was excited to, this was very good and interesting. This warrior who are seeing there is the Minister of Education from the country of Suriname. So I'm going to give you the next pop quiz. Suriname. It's in the which continent is it in? Let's see. There's 100 people here. Which continent is it in? Let me see if you guys can help me with Jeopardy. Okay, I don't see South America. Great. Okay, South America. Very good. Okay, now here's the tougher question. What language do they speak? What language do they speak? Oh, wow. Dutch. Not many people know that. It's one of the only countries outside Europe that actually speaks Dutch. And they're bordered by French on the one side, French Guiana. On the other side is English Guiana. They speak English, and they're bordered on the south by Brazil. Portuguese. Now, I just told you 4 countries that don't speak, none of them, and they are in South America. They don't speak Spanish. There are different languages. So now what I wanted you to understand here is the idea. So this is the Minister of Education, a very good friend of mine. And this minister and the health minister were at 2 ends. The Minister of Education wanted to start school, and the health minister wanted to be careful, wanted to focus on safety. And so they agreed that they are going to focus on safety when the school opens. And then one of the decisions the country made was they just passed all the children in all the grade levels, 7th grade, 8th grade, 9th grade. And they did not do the last quarter of the whole school. So the minister asked me, they missed all the mathematics. Can we find a way to actually get them to think about mathematics? But the Minister of Health wants to do focus on safety. I said, that's great. Tell me what they're focusing on. She said, face masks, social distancing, and hand washing. I said, that's great. Let's create a new course on mathematical modeling of safety. And that's now in the curriculum of this country, just to let you know how you should take advantage of, and try to make impact if you can. So this is the trial, and this is now being practiced, and several teachers in the country are being trained on this idea of how to bring safety and mathematics, for example, together. Now they're going to try it on other subjects. I did tell you about the Sustainable Development Goals. COVID has impacted so many other things. For example, Uber, there are 75 million riders, 3 million Uber drivers. Imagine what happened to those drivers when COVID hit. So jobs were lost. That's one of the goals of the Sustainable SDGs. I focus mostly on the good health and well-being. Our paper just got accepted this week with one of our colleagues at Mason, Dr. Connie McNeely. And this is about challenges that COVID has posed, focusing mostly on the health and all the other aspects. And happy to send if anybody wants to read that. And we also wrote another paper which impact how COVID-19 impacts everything else. And sometimes if you don't see the connections, you create wrong models. So finally, I saw Tom, and I saw some folks I recognize. So we have formed the only way to solve these big challenges and come up with real good models and all that is to go back all the way to high school and earlier and work with teachers and actually build on better pedagogical practices. So we partnered with several school districts, and actually through a Virginia Department of Education grant to actually help understand what is data science, what is computational thinking, how do you create models and things like that. So it is done at all levels. So those were some of my projects. And then one of the other things I did was we ran a workshop series. This is another way you can actually engage the globe. 23 countries participated, over 1,000 participants. We did 5 webinars, We brought experts in different areas, for example, non-pharmaceutical interventions like face masks, social distancing, data science, and different types of things. This was also a collaboration between multiple institutions. I did it for 5 webinars, and which ended with a conference last week, and really, lots of information shared across the globe. So I want to start off the next phase with the following. Is a very famous quote by a British statistician who's very well known for his quote, which says, "All models are wrong, but some are useful." George Box. It's a very, very powerful thing, and I always wonder what he meant by that. So of course, the idea is that of this quote is that every single model will be wrong, meaning that it'll never represent the exact real behavior. We can see that. But having said that, even if a model cannot describe exactly the reality, it could be very helpful if it is close enough. That close enough is the most important thing. And so I started to really take this statement very, very seriously. I always do that. And then I see reports like this. This was published back in April, first week of April, from Colorado School of Public Health, which predicted the importance of social distancing, extremely, extremely important. And which basically said something like 60%, it'll be 60, social distancing is 60% effective. And they gave these nice numbers, like, if you're doing 60% effective, then you only have this many infections, 65,000 infections. If you're 40% effective, then it can double, and, so on. And so it was very interesting that they projected this. And you can go back and look at the numbers that they projected, and you can see on the screen. And then you realize, wait a minute, now we are having about 200,000 a day. And then you start to realize something is not correct here. And, this was all predictions. And then it started making me think about looking at these CDC numbers. This is from yesterday. CDC numbers. I'm starting to think, wait a minute, all the models are wrong, but some are useful. And this is when I start to realize what could have gone wrong. Was it the model? Was it was it like the approximations in the model? What was actually wrong? And so on. So, and, it's very important to understand that, there could be so many other things. For example, maybe we didn't take advantage of, resources, capacity in the hospitals, and maybe people did not practice the policy like social distancing and things like that. So all those different things could have gone wrong, which made the, and maybe there are certain things in the model we don't understand, or nobody talks about it, and it's just people just use it because it's black boxes. And this is a very common problem, by the way. Okay. And so I just, you may hate me for this, but I reframed George Box's quote. Here's my quote: "All models are wrong, but some are more wrong than the others." Okay. And I started to practice this, and I'll try to finish on a positive note later, but it has helped me to start like this. So let me actually help model, and some of you may have done this, but it's very useful to see how things can actually be modeled. And I'll use very simple example, piano tuner. And if I ask you the question, how many piano tuners are in Chicago? Model this, okay? And the first question you are wondering is like, wait a minute, what type of question is this? Will this be on the exam? You need to give me more information. Well, I'll give you one information. I'm going to tell you that in Chicago, there are 3 million people. Now that's it. You don't know anything else. Now imagine I'm trying to model COVID. This is the same type of idea, some crude modeling. And so I have to make assumptions. So now we are talking about a piano tuner, a person that goes to somebody's house, repairs a piano, and then comes back, basically. So if you think about it, I can start to make assumptions. So I can say like, okay, maybe there is a family, most families, let's say mom, dad, and 2 kids. That's 4 people in a family. So if that's the assumption that we are making, 4 people in a family, then I can divide by 4 and I get 750 families. Now I can say not everybody can have a piano. Maybe every 5th house has a piano. So then I can go ahead and say, okay, every 5th house. So let me go ahead and divide this by every 5th house. Now we know how many pianos are there in Chicago. By the way, this is all crude estimates, okay? And then I make an assumption about what a piano tuner actually does. Well, I drive to one end of Chicago, Aurora. I drive to another end of Chicago. You know, the traffic in Fairfax and all that stuff. So by the time I finish 2 of the jobs, it's lunchtime. Then I have to eat lunch. And then I go and do 2 more jobs. So maybe I can do 4 jobs a day. And I work a week, and to me, a week is not 7 days, even though I work 7 days, but let's suppose I don't work on Saturday and Sunday. I only work on 5 days. Now you need to notice how I'm estimating here. I'm saying 4 jobs a day, 5 days a week, that's 20. I'm using nice numbers because it's easy to calculate. Now, 20 jobs a week. How many weeks are in a year? Of course, you're going to say 52. Of course, please take some vacation this winter. So 2 weeks vacation, let's say I'm going to take. Once again, notice what I did. Instead of 52 weeks, I'm using 50 weeks. Now let's do this again. A person does 4 jobs a day, 5 days, that's 20 jobs a week. 50 weeks, that's 1,000 jobs. So essentially, if you think about it, number of pianos serviced is 1,000. So now, if you think about it, the total number of piano tuners, a rough estimate is 150. Now go and check Google for yourself and find out what the actual number is, and you'll be pleasantly surprised that this is not too far off. Then you start to wonder, wait a minute, did we have to do all that fancy computer simulations to create models? Not really. Sometimes intuitive knowledge, I mean, something that you know is very important. Now, what did this teach us? Well, if you see this picture here, can somebody type on the chat, what do you see? Just type whatever comes to your mind. Go ahead and tell me what you see. What is coming to your mind when you see this? Dots, perfect, Malda. Anyone else? Bubbles, okay, very nice. I like bubbles, yes. Colored bubbles, Tom. So that's great. Raindrops on oh wow, you're very creative. So that's very, very interesting that you all solutions. This must be a chemistry person. So that's great. So that's great that you all have these different things. But what you're actually bringing to the table is your knowledge from different expertise, maybe chemistry, maybe like, what you're seeing. But when you actually connect the dots, to me, it is cities connected by streets, for example. Now, this is where data science starts to become very important. What type of linkages that you give, and then the models that come out of those things. That's very, very important. And of course, this can be differently connected and all that stuff. Now, we can go one step further. So that brings experience. You're bringing experience, knowledge to experience. Now, this third category I'm going to show, don't worry if you did not see it. How many of you saw the cat here? Well, maybe you did not, which is okay. That creativity part is what we want to build in our future workforce, in terms of thinking about modeling and all that stuff. If you did not see the cat, don't worry. I never saw the cat at all. I'm not that creative. But the whole idea is if you can actually figure out all these, competencies. So now how do you translate this into a classroom? Well, I was teaching this class last semester, and some of the students I see have taken this class, but and I was supposed to, engage them in some other projects, and COVID hit. And so I had to go completely online, but then the students were also very impacted, but they said, Dr. Sesher, we want to do some real projects and all that stuff. I said, okay, great. We all know what's going on with the ventilators and hospital capacity. Why don't you do my Fermi problem on this Washington Post article? Now, when you connect things like this from an article to the real thing that they're learning in a classroom, trust me, you are just creating individuals that are going to be the future best modelers. And this is the type of thing, they can make mistakes. That's okay. The question is, so I had to ask them to find the number of ventilators. It's amazing how their thinking capacity went. Okay. Now you can try things like this, very simple things like this in whatever workforce you are in. So that students don't always say like, what is going on? When am I ever going to use this and things like that? So, instead of just showing curves and things like that, it's very important to do that. And so those of you, this is a pitch. If anybody is interested in taking this class, I teach this in spring, and it's COS 400. And for graduate students, it's COS 600. They will be leaving my class with a lot of these types of competencies. Fermi is just one of them. I know some of you have taken this class before from me, and they will take these challenges. So now I want to switch gears and take maybe 10 more minutes if it's okay, and wrap up. So essentially we have seen some problem solving and models. I want to now talk about all the challenges that is happening in terms of to model any of these diseases. We really need to understand the origin of these diseases. I like to go back and study what happened before. So of course everybody goes back to the Spanish flu. So if we go back to the Spanish flu, it was pretty serious in 1918, and it was believed to be a bacterial disease, but it was spreading not until 1933. The influenza started to spread in humans through a virus, and then what happened after that. So, but then what was interesting is the two graphs that I'm showing is of Philadelphia and St. Louis. Now, Philadelphia waited 2 weeks after the first case happened. And this was back in the Spanish flu. And you can see the number of deaths that happened in Philadelphia. But then St. Louis implemented it within 2 days. And you can see what happens to the curve. It moved to the right and it actually came down. And this is what people popularly call as flattening the curve. So I'm sure you're seeing this in the news all the time, flattening the curve, flattening the curve. Unfortunately, when we are modeling flattening the curve, what should you do to flatten the curve? This is where the modelers sometimes forget to do something very important. So if you're looking at my graph right there, flattening the curve, yes, getting the peaks down, you can do this by reducing transmission rates, implementing social distancing policies, face masks, all these things. You can put it in the model and all that stuff. But look at the bar, little dotted bar that is racing. That is the hospital capacity, the number of beds needed, the number of PPEs needed, the number of doctors needed. If you do not model that in conjunction with the other thing, then there's no point. You have to really understand how to balance the two. This is where models become important. So, and if you go back and study different types of diseases that have happened in the past, from the Spanish flu all the way to, COVID, of course, one of the biggest ones that we recently had, in the past, like over 15,000 deaths, was swine flu. And there were also big ones like Hong Kong flu, which was 200 deaths, but it was localized in Hong Kong, or Russian flu, which was localized in Russia. But what makes COVID interesting is it spreads across the world. Now, that is the part that many people really don't understand. It's like, what is the big difference? And this is where experts like Lance is trying to make a difference in terms of understanding what is interesting about the virus. Now, if you all see the timeline of what happened in the color coding here is how models evolved actually. So, people started with very simple epidemic models, something like SIR models. And then they realized, oh, this is not a regular event. This is a super spreader. They defined super spreader and they added something more to the model. And then they said, oh, now we want to use intervention, social distancing and all these things. Let's add that to the model. And then they started realizing that developing countries are having higher mortality, and some of the even developed countries started having higher mortalities. And then they started realizing hospital capacity. Then they added that into the model. And so this idea of a model evolution is very, very important, that changing over time, but you have to do it in the right way. And I also noticed that people like to use these terminology. We need to be really careful when we are using like COVID spreads like wildfire or spreading like a wave. These are not, you have to be very clear in the modeling lingo. Fires are like a forest fire can flare up anytime. So I have to model that anytime as a spike. It's a mathematical function. If you don't understand, if you just randomly say things like wildfire, what does the model reflect the wildfire nature of COVID? If you say a wave comes in a very periodic fashion, right? So, you have to really understand, and it dissipates and things like that. You got to bring that into the model. So when the press and all these newspapers are using these words, I hope they will consult with people and then put a model by some university or somebody like that. Please put the language and the models and the mathematics or things together. We need to present it in an educated fashion. This is to all the journalists that are out there. I know you are all doing a good job, but please make sure you really understand, just don't hear the public health perspective, hear a modeler's perspective, hear somebody from a different area, and then talk about it. And then the two very important things that everybody is concerned about is the R0, R0, R0. This is like the basic reproduction number. Basically, it tells you how contagious a disease is. Basically, how does a single infected individual cause secondary infections? That's basically a number that is calculated by these models. The second one has to do with how virulent it is, how dangerous it is, basically. So it's called the case fatality rate, CFR otherwise. So for every disease, this is there, and it all depends on how it spreads. If it is like, aerosol, like measles, it can go long distance. So the R0 can be very high. If it is like COVID, it's thick, the heavy droplets, so it can only go so far. You got to model these things. Many models miss these important things, and they produce all sorts of numbers. We need to be very clear with these types of things. Again, those are, I'm presenting it as, it could be a myth otherwise. That's the problem. And so the other big myth, people know basic reproduction number, and everybody left and right uses that word basic reproduction number. It turns out there's different types of basic reproduction number. Basic reproduction number is the reproduction number that you calculate at the onset of the disease. But an effective reproduction number is the one that you calculate over time. So people don't use those. Those are different ways you compute these things. Again, for those people that are using these things, please understand what you are presenting. It's very, very important. Communication is extremely important here. So what you use to present, because at the end of the day, you don't want it to go into fake news or, things that don't make any sense. Like Lance was saying, don't believe the science. That's the most important thing, but understand the science. I'm not saying understand the equations, understand the difference of these types of simple things and all that. I may not have time for this. Here's a classic mistake that happened. For example, modeling. Let's say you have the community and a long-term care facility. This is like in a community. Let's say Fairfax County, and there is a long-term care facility. So what you're seeing are entries inside the matrix where a community interacting with a community gives you 0.8. Remember, the R0 has to be less than 1 for the epidemic not to spread, basically. So I'm looking at these numbers and saying, oh, community interacting with community is only 0.8. Community with long-term care facility is 0.2. Community with long-term care facility with when they interact with community, when they go see the visitors and all that. So these numbers are very small or less than 1. So there should be no epidemic. And everybody signs off on it. Policymakers saying, oh, it's great, Fairfax County, blah, blah, blah. But then now you realize this is not for Fairfax County. This is for another county, by the way. So then you realize, let's work out a simple example. And this is where modelers come in, okay? Let's understand the infected cases. Let's suppose there are 100 infected cases in a long-term care facility and 1,000. I'm going to make the math very simple. 1,000 infected cases in a community. Well, let's take these 0.8 of them. That is going to be, so let's use that same ratio. So 0.7 of the 100, which is 70 people in the long-term care facilities, create new secondary cases. 0.2 of the 100, that's 20 secondary cases. And so you calculate all the secondary cases. Great. Now, what do you do then is basically, you simply count the total number of cases. If you the secondary cases, that's 1290. Then you realize, wait a minute, the number of secondary cases ratio with the number of primary cases is what you need to define to do R0. For the community as a whole, with the long-term care facility, it is an epidemic. So here is where models can fail if we don't understand and we do things just based on what we see. Okay, and so my final set of slides is, biological modeler, maybe model is a mouse or model is a virus. For a mathematical model, it's usually equations. And then the data, very important to link what you see around you to actually the equations or what the experiments are proposing. And then you decide on the policy. And of course, this is a non-linear aspect. So you could go back and at each step, you can have interventions. You could do analysis, not just statistical analysis, mathematical analysis. Another confusion. When people think data science, they think it's all statistics. My big giveaway for you, it's not, okay? And trust me on this, it's not all statisticians, claiming data science as their thing. It's not their thing, or it's nobody's thing. Data science, data analytics, data-driven business may claim that it's data-driven business decision-making. Well, it may be great for having degrees and courses, but it's not. You have to come together to really work together to solve a problem. It doesn't matter which college or which background you have. So the most important thing is we should not think like, oh, one person gives it to two people gives it to four people gives it to, yes, that's an exponential model. It's great to teach children, but COVID taught us that it is a super spreader. That means, one can go to 10. Then each one can give 10 more, and the spread is so quick that the entire population can actually go through this. Now, this can be tracked through what is called as a queuing theory. Very nice and lots and lots of models. CDC models are actually using this. It's a very powerful thing. It uses it's analysis of waiting lines. So like hospital beds, and you are actually going to the hospital. How many patients are arriving in a queue? What is the average wait time? What is it? How does it vary during the day? There is a formula for it. And then you try to incorporate that into your models and things like that and make predictions. So it's a very popular model that is being used, but there are still drawbacks. And then there is lots of questions, but how do you think about age structure? How do you think about drugs, vaccines, and all these different questions that are out there? And then there's testing. So I'm glad like experts like, Lance are around to just tell us and teach us so many great things about testing. But I do have to tell you, I've been watching and working with lots of developing countries. There's lots of issues. There's only so many doctors. There's only so many people in the staff that can actually do the testing. So what is happening? Errors. in testing are happening. I'm not talking about experimental. I'm sure, Lance and his group and everyone else in the world are so thorough with their work, but what is happening is the reporting. And what do I mean by that is how it is being reported. That means it's a very important thing to understand that there are two types of outcomes of the test. One is called test sensitivity, and one is called test specificity. So when people are infected and they are showing positive, then they are true positives, like the picture is showing. People are infected and they're negative, then they are, that means they're false negatives. And, then you have not infected showing positive, that's false positives. And so then true negatives. So you can group these people based on coming in and taking tests and all that. The unfortunate thing is when you calculate this thing called sensitivity, you take the ratio of, it's basically the ability of a test to correctly identify those with the disease. So which is the true positive rate. So for that, you have to actually divide all the true positives that you see there by all the number infected. The problem is we don't know the denominator. We don't know how many people are infected. We only go by the reporting, who reports and things like that. So you can't really trust that all the time. And then the specificity is the ability for the test to actually correctly identify those without the disease. So this is basically true negative rate. And so this has to do with those true negatives divided by the number of healthy people. So again, these are all simple ratios. I mean, we can give it to fifth graders to do this thing. But the point is, if you don't have the right data, then you're calculating wrong numbers. So these are, more than myths actually. And final slide, I want to just leave you with this potential pandemics, that possibilities that has been predicted, the second wave, the third wave, and multiple waves. So there's several things that have been predicted in terms of how the waves are going. It's basically the sudden spread. This is a model that we are actually seeing. That's the second model. This was predicted, by the way, back in April or May from Harvard Chan School. So and then some are also predicting slow burn, like mixing with flu and then having a slow burn. So models should try to reproduce these types of things and all that. So finally, we need to not just do models like create a compartment, write equations, simulate pictures. We also need to bring in what do we learn from this and how can we make our models better. This aspect is one of my research areas where we published one of the first papers in deep learning for infectious diseases with one of the fastest algorithms. And essentially, how do you use neural networks and all the state-of-the-art ideas to actually go back to the model and say, hey, we need to update this. Andrea, I'm going to stop there. Thank you.
Thank you so much, Padu. That was very interesting. And hopefully, for those of us that are not mathematical modelers, we have an appreciation for the complexity and perhaps a little more patience with the varying models that we see. I think sometimes the public thinks, science is one and done. And as both Dr. Leota and Dr. Seshire clearly delineated, it's an ongoing process and things are being updated. So sometimes when you hear public information and then you hear something contrary, it's not really contrary, it's just updated, right? So as you speak to people around your neighborhood and your families, that's the process of science. That's what science is. So now we're going to answer some of your wonderful questions that you've submitted, and we're going to alternate some of the ones that you've submitted in this session as well as some that were submitted online. So here's one from Anna, and I think Anna is a George Mason student. The COVID cases have disproportionately been blamed on young college students. Is this actually the case? Either one.
So from a modeling perspective, are you asking at George Mason or in general?
It doesn't specify.
In general. Okay, so one of the things that has been, the models that have been, so if you take these SCIR, whatever models, if you group them by age clusters, China has some models that was released earlier. And so these models, and then Colombia has some models related to that. What they have done is these called age structure models. And yes, they have done groupings. That initial thing, they did not see a whole lot of things. Where they actually saw was when they actually visited healthcare facilities. So there are now new models. In fact, we are working on one model which will be submitted for a journal publication soon, where community, lots of youngsters from the community going to the healthcare facilities and either giving the disease or picking up the disease and coming back into the community. It turns out that this, they are noticing there is a lot of, there is data that suggests that if they don't wear face masks, so the behavior, because when you go to a healthcare facility, the folks there are better behaved. They're mostly with face mask and things like that. But the younger people sometimes don't know. Even children, they want to go hug grandparents and things like that. So what happens is they may get the disease. But again, the biological side, Lance is the expert. The models do see these types of, but in terms of the effect on how it impacts them in biologically, maybe Lance, you have an answer to that.
If the question is how significant is infections in the college campus, bringing them back to society or their parents or their grandparents, it's low. We know that infections in elementary schools, that is also a low rate of transmission to society. The main transmission takes place in when you have social groupings, such as in restaurants and bars and parties, and that is where most of the transmission takes place, or in congregations. And it recently been modeled, as Padu talked about, that simple social distancing makes a big difference, reducing the amount of individuals attending a party to 1/4 of what we think we might want to have, like 10 people, makes a big difference, or 1/4 of the restaurant being open. Those are really more important than transmission from schools, those types of social activities. But even if an individual is sick with the virus, they have a very low chance of spreading it if they wear a mask and the other potential person that they could transmit it to also wears a mask. So we still have to know that the greatest way to prevent is by masks and social distancing.
Well, speaking from somebody that was just at the Dallas-Fort Worth Airport, I'm glad to hear that. So I wore my heavy-duty mask. All right, here's one from one of our faculty members, Dr. Robert Ehrlich. This is a question, he says, for Dr. Leota. I noticed that on a per 100,000 population basis, the US current infection rate is pretty much the same as Germany, France, Spain, and Italy, all of which have risen significantly, I guess, lately. I had thought Germany was doing a much better job at limiting infections than us. Does my observation suggest that mitigation measures are of limited value, or alternatively, that the Germans have become as careless as we in the United States? Do the tiny infection rates in China, Japan, and South Korea suggest a genetic component of susceptibility to COVID?
So there's multiple questions in that question. One is whether the United States is doing better than other countries. And as you know, the number of deaths, the deaths in the United States is greater than 250,000 compared to the other countries, which have much fewer numbers of deaths. But maybe if you count it to the number, per capita, you might see that we're more similar to other countries. That's what some people want to say, that we're doing okay in the United States. Any deaths are not acceptable, in my opinion, as a physician. And so I think if we focus too hard on whether we're doing successfully and how we compare to other countries, then we should not get distracted by that. We know that social distancing works. We know that mask wearing works. And in terms of the genetic susceptibility, indeed, there is some slight tendency for different genetic backgrounds to affect the severity of the coronavirus disease, but it's been hard to tease that out specifically. So we don't know for sure. There's some hints about it, but it's not, it's not definitive. And there are 6 types or strains of the virus around the world, and we can track where viruses originate. So mainly comes from China and then spreads through the other countries. We can track them by the strains of the virus, but we don't see much difference in the behavior of those strains. We think overall, though, to get to the implication of your question, is that the death rate all over the world has, per capita, has started going down. Some cases it's more than 20%, other cases it's less than 20%, but the death rate goes down because we can treat the disease better, we know how to treat it better, but also it's thought by virologists that the virus is adapting to humans. And if a virus that spreads faster is one that doesn't kill as many people, because then there's less to spread from. So in all viruses of this type over time, over many years, they become less and less virulent for that reason. So there, we might be seeing some reduction in the virulence of the virus, or as it goes through a population and comes out the other end, it might be reduced in its death rate. Overall, we think that the reduced death rate is a combination of multiple factors, which gives us a lot of hope. We don't think that some of these other variations in the virus, the 6 strains throughout countries, and even variations in individual susceptibility will make a big impact on the virus vaccines. We think they're going to work on all parts of the population in all countries. This is what virologists hope, based on the data we have. So I'm sort of answering a lot of questions that this one good question implies in regarding to many different aspects of the susceptibility.
Thank you. Here's a question from one of our audience members. We have several questions about the vaccine, so we may want to handle those quickly. Is it likely that COVID-19 vaccine would need to be taken annually like the flu shot?
We know that the vaccine, at least the current ones, have to be done twice. And then a first vaccine, then a booster. We don't know how long the immunity lasts, because when a vaccine often may not be as lasting or as strong as the natural infection itself. Because when you're naturally infected, you make antibodies against all different parts of the virus, as I pointed out. Whereas when you have a vaccine, it's just against one little part. On the other hand, the success of these vaccines has been much greater than we hoped for. So it might be easier to have a successful vaccine against this virus than we ever thought. And as you know, it's similar to it's just a variation on a cold virus. And when you get a cold, you get over it and you're immune to it. You never get that same strain of the cold virus again. So we want to hope that it will be like a polio vaccine, like a vaccine for measles, that it will be long lasting after it goes into the memory cells of your body. But of course, we don't know for sure. The only thing we can say with excitement is that it's looking better than we ever expected so far.
So, Padu, we need to, let's unmute.
If I can add to that quickly, I think this is a place where models can really help, because if we do have, say, a reasonable model that is close to tracking data, we can actually predict the time that is. So again, based on what we have, we can add a vaccination compartment and actually, try to understand the relationships, and then we can expand the model and actually try to predict these types of times and tell the experimentalists saying, this is what the models are telling, so.
So that follows up with Padu, a question that is related to mathematical modeling. The media keeps showing that more and more people die day by day all over the world, yet they don't talk about how many people survived it. Of course, there's the asymptomatic people that we don't know. In your opinion, based on the vaccines, the world's doctors and scientists, how long do you think it will take for a vaccine to be fully successful? So I'm guessing they mean in conferring kind of herd immunity that we've heard
Right,
about?
herd immunity is one, and also those parameters that I was talking about, the transmission parameters. It's all based on how many times they come in contact, and how often how big that contact transmission rate is, and the probability that it will get transferred to the next person. Similarly, for the vaccine, we can define a parameter that talks about how effective it is going to be. And then we can actually see what, based on all the other things, like, if they're quarantining correctly, if they're isolating correctly, if they're doing all that thing, the models will predict, that particular parameter, and, the best values for those parameters. It's called parameter identification. So I think this is, and then it can tell us, backtrack and tell us about the time, in days or in months and things like that.
So hopefully people will want to get vaccinated. That's certainly going to help.
Yes.
Yes, I think that's an issue, is whether people should, when it comes out, should they take it or wait to see how safe it is?
That's right.
This is where competition is really important, because we have all these companies developing vaccines, and we're going to have a lot of scientific data. So listen to the scientists and look at the data. And as scientists, we're just as skeptical as you might be about whether a vaccine is going to work or not, or be safe or not. We're going to scrutinize that data, and and then once it's peer reviewed by other scientists who give it the okay, it's highly likely that it will be safe and effective. But all of us believe that it should go to the most susceptible individuals first. It should go to the elderly. It should, just like we had a small number of vaccines for the influenza, we'd use it for the elderly. We'd use it for the people who have underlying conditions. We want to make sure that at least they get access to it first. And because we have, those are what we're all trying to protect from getting infected. And so I'm optimistic. I'm very optimistic looking at how much we're learning about how this virus works. But we've had many surprises and many setbacks in the pandemic. So we don't know what's really going to happen. Overall, we're getting better and better at treating this disease. And so I want everyone to have an optimistic viewpoint.
So we have quite a number of questions, but I want to tell the audience members that if we don't get to your question, we will post this video on Galileo Science Cafe website, and I'll give you the link for that shortly. And also Carrie is going to send a follow-up email with the website address. You have a fellow Mythbuster. You've recruited somebody. Here's a great question. Great presentation, thank you. How can we explain to the non-scientists around us to ease their fears about RNA and DNA vaccines? Many are worried about claims that those vaccines will change our DNA.
Well, this is an RNA virus. It's different than HIV, which is a DNA virus. The RNA viruses, the RNA does not get integrated into your DNA. It just stays outside the nucleus in the cytoplasm, and it's used to make more viruses. So it's not passed on in your genome like a DNA virus is. So that's one good thing about the RNA virus. It doesn't leave any traces in your genes for this RNA virus. So that's and the RNA vaccine is just a small piece of RNA, and all it does is produce a small piece of the virus protein. And so it lacks a lot of other potential toxic parts of RNA, and it's just a really short stretch. So we hope that it will have low toxicity. Some individuals have worried that the particle that we use to deliver are in some cases a defective adenovirus. A virus is used to deliver the vaccine. Some people worry that in itself, separate from the vaccine components, will cause side effects. And that has been carefully looked at. We do not see significant safety concerns in the patients so far, so we're hopeful. Also, we see that different vaccine companies have different types of delivery mechanisms to get the RNA or the protein delivered to your body. And so if some of these other components of the vaccine have toxic effects, this should pop up immediately when we see the data from these different companies. So for example, if somebody has an adenovirus vaccine, we might see more toxicity from that compared to a different vaccine that has this has the other components are the same. They're just using a different way to deliver that vaccine. We'll immediately see that difference and we'll be able to correlate that with how the vaccine is put together. So that is why with all this competition and everybody trying to have a safe vaccine, that science is going to win and the public is going to be able to have a lot of choices. And so you will hopefully be able to choose from the very safest data to pick the vaccine that you want.
And from a data science perspective, I'll just add that as the algorithms are getting so good, the computational power is becoming so good. I'm sure as the experiments are getting better and better, the computational algorithms are getting super good also. So we will definitely be able to, from that perspective also, it's going to be a good thing. So
just our advice is keep looking at the scientific data. Don't listen to what's in a website or on the web, because that's why science usually marches on and gives the truth, because we're all competing and have highly critical peer review of every data that comes out. And we're not going to let any false data be revealed. And also in this regard, one of the best aspects of science is maintained. That is reproducibility. Another scientist finding the same thing that I found. If I have a hypothesis, I can be very excited about it, but unless it's proven by somebody else who uses an independent lab and they get the same result, then no matter how much I believe in it, I can't know whether it's true. Since we have all these scientists and all these vaccine companies all working towards the goal, we're going to have many different data points to compare and see if everybody gets the same results. Then we can trust it. So that's why sure, it can be dire. We can be very worried about our loved ones being susceptible to the virus, but at the same time, we can see that science is making so much advances that that we're going to have some good choices as time goes on, and the solid working vaccines that are safe will win out over the other vaccines over time, and we'll know it.
Great. I think we have time for one more question. And these have to do with the virus. Does the virus cure you or prevent you from catching COVID? And similarly, if people have already been infected and recovered from COVID, do they need a vaccine?
This is a good question. We are going to be measuring the antibody levels in 1,000 asymptomatic students. We want to do large-scale measurement of antibodies to give us some data, like Purdue says we lack. What is the percentage of individuals that have previously been infected and now have antibodies to prove that they had it in the past? They might not be we might not need to give them the vaccine, at least in the first round. I don't think the vaccine is going to hurt them if they've had it before. It will stimulate their immune system to, they say, I already saw this, and it'll rev up their immune system. I don't think it's going to be harmful, but I think that we need to know more by antibody testing about who really has had it in the past.
All right. Well, we're closing up on our time, and really appreciate all of you coming and asking great questions, and we will address those questions and give you the answers if we didn't have time to address your particular question. We'd like to thank Dr. Seshire and Dr. Leota for a wonderful presentation, very clear, very accessible, and so much to think about. And it's so exciting to see what wonderful work Mason is doing. And right in our own backyard, they're spending so much time being so careful and taking really good care of the world and especially our community. So thank you so much.
Thank you, Andrea. Thank you.
Thank you. Thank you.
I do want to share one last slide, and that is about our next, let's see where it is. Here it is. Our next session. Let's see where it is. Okay, here it is. Okay, can you guys see this? Join us next time. Okay, so one of the requests that we had from our audience members was neuroscience. And Mason has a wonderful interdisciplinary neuroscience program that integrates with mathematics, School of Systems Biology, biology, psychology, and so forth. It's very interesting, and it's right before Valentine's Day. Dr. Frank Kruger is going to talk about the neuroscience of trust. So he's actually an editor on an interesting new journal that has to do with trust and economic development. So it has widespread implications. He uses fMRI data to understand what the brain is doing in situations where people are trustful or not trustful. So I think it's something that you'll all enjoy, and we will be sure to send a note to you. So thank you so much. Thank you, Michael Galvin and Carrie, for helping us, and we hope you have a wonderful and safe Thanksgiving holiday.
Thank you, everyone. Be safe and healthy.
Thank you all. Thank you, Michael. Thank you, Kerry. Thank you.
Bye-bye.